I'm now recording. Good. So to recap then, sound waves in musical instruments also create standing waves, just like the ones on a string that we were discussing last time. And for most situations, the relationship is the same as we introduced last time. The wavelength relationship is the wavelength of the nth harmonic is 2. Oh, brother. 2L over n, where n is a harmonic number. Like that. The exception to this is if we have a sound tube with one end closed and the other end open. Then we had a different wavelength relationship, 4L over n, where n was only odd numbers. Now, both of those relationships are given on the formula on the data page. Of course, it's up to you to remember to which situations they apply. Let us turn next to an example. So this will be update 94. Change the slide now. I think you already had this in the video. I'm just going through it again. So what have we got here? We've got a tube that's open on both ends. Okay, so there is the significant information. It's open on both ends. And it's in its fundamental mode. Now, fundamental means lowest harmonic means n equals 1. Because it's open on both ends, open, open, and closed, closed, both have the wavelength relationship, just like on a string, 2L over n. Here we have the length of the tube, 0.3 meters, and here we have the speed of sound. All right, we're asked for the frequency. So first, we'll find the wavelength. Wavelength is lambda. So we get 0.6 meters using the standing wave relationship. We are asked for frequency. Frequency is F. We'll find that using the wave equation. Lambda F is V. So that means the frequency is V over lambda. The speed of sound is given. And we just calculated lambda. So we get 567 hertz. 566.6. And a hertz is just a cycle per second or a reciprocal second, which is what you get out of these units. Alrighty, so those relationships should be familiar to us now. Let us then just look ahead a bit and go to the bottom of page 97, please. So there's just a summary again of the various relationships for sound waves there. So I'm going to change the slide, page 97. Okay, so I already recapped these wavelength relationships. In addition to that, for sound, of course, we've got the period and frequency relation that applies to all waves. For the speed relationship for sound waves, it just depends on the temperature of the air. And we had a relationship last time for the speed of waves on a string that was dependent on tension and linear density, but these are for sound waves, so we have a different speed relationship. And then for the energy of the sound wave, we had an intensity equation. So this tells you how much power, sound wave power per unit area of receiver. And so it depends on the density of the medium, which could be air, or the sound wave could be traveling through water or a solid, for instance. Omega, the rate of vibration. And remember from the period frequency relationship that omega is really just another way of measuring the frequency of a wave. So intensity depends on omega and on frequency. Amplitude is how much the air molecule is moving back and forth, and V, of course, is just the speed of sound. So that's the intensity of the sound wave, which is related to energy, of course, because power is energy per second. And then the pressure amplitude, how much the pressure is going up and down in the sound pressure wave, depends on, again, the density of the fluid the sound wave is traveling through, how much the air molecules are moving back and forth, that's amplitude, the speed of the sound wave, and the rate of vibration. Okay, so that's to recap those quantities. We're now going to turn to the next page, please, which is page 98, and we'll do an example. So I'll change the slide now. Okay, so what are we asked for here? We're asked to find the intensity. Intensity is I in watts per square meter. And we're asked to find the pressure variation. That'll be in pascals. That's just how much the air pressure goes up and down at a given point due to a sound wave. Okay, we have the frequency F is 250 hertz. And we have the amplitude of air molecule motion is 1.2 microns. Now on my page, this isn't showing up clearly, but I'm pretty sure it's okay on yours. This should be 1.2 times 10 to the power minus 6. Alrighty, so let's see. So we want to find the intensity of this sound wave in watts per square meter. And so 1/2 rho omega squared A squared V. So we've got the density of air, but we don't have omega and we don't have V. So we're going to have to find omega. Well, that's pretty easy because period is reciprocal frequency is 2 pi over omega. So omega is 2 pi F. And the frequency is given as 250. So this is just like 1571. And it has units of radians per second. We'll also have to find the speed of that sound wave. Again, it depends on air temperature, which is given. Now that temperature is in degrees centigrade, and it was given as 20 C. So there we are. So we're now ready to substitute in. So we put in rho, the density of the air. Now radian, it should be noted, is dimensionless. So this radian just cancels out when there's something else there. So we gotta be careful here. 1.2 times 10 to the power minus 6 is the amplitude. We have to remember to square that. And then finally, the speed, 343 meters per second. So I suppose we should mention the units here. So the number will work out fairly straightforward as long as you punch it in correctly. So it'll be 7.85 times 10 to the power minus 4. Could somebody just type something in chat just to make sure that you're still with me here? Am I coming through okay? All right, fantastic. Thank you so much. So yes, what will we have here? So we're going to have kilogram. We'll have meters squared from this bracket, and then per second there. And then I'll cancel this meter out here, this meter, and I'll make this meter squared because I need meters squared at the end of this. And then I'll just leave that over there. Oh, sorry, and it's actually seconds squared. So I'll leave it as per second. So a kilogram, sorry, there's another second in the bottom there. Okay, so there's actually 3 seconds. Okay, 2 seconds here, second squared, another second. That's good because I need that. So a kilogram meter per second squared is a Newton. So this is a Newton meter, which is a joule. Okay, this is a joule. A joule per second is a watt. And so we've got units of watts per meter squared, which is exactly what we should have for a unit of intensity. So there, we did the units. Next, we want to find the pressure fluctuation or amplitude. We know it's 101.325, but of course, as the sound wave goes through, the air molecules get closer together or further apart, so the pressure goes up and down. Density of the air, amplitude of air molecule motion, speed of the sound wave, rate of vibration of the sound wave. So we substitute. And I'll get 0.83 pascals, but maybe somebody could check that for me. Very good. So there's example 3. And that's just some experience with the energy relationships. How much energy a sound wave has. We're going to do just a few more examples here together. There's quite a lot of little topics here. Okay, I believe the next thing we did is we said, all right, so sound intensity varies over quite a few orders of magnitude. So it's helpful to introduce a logarithmic scale. So that logarithmic scale is introduced on, oh, hold on, we don't quite want to go there just yet. We need to turn to the next page, page 99, because I believe I sort of set up an example and might not have completely finished it. So let's please just turn to the next page there. Is it this one? Yes. Okay. So here on this page here, so first of all, we had the intensity of a point source of sound. So the point source is emitting a certain amount of sound power, and that sound wave will spread out over the surface of the sphere. So that's the relevant area right there. And so in this question here, example 4, I believe we had it mostly finished. So here was somebody singing, right? So here's the source of sound. And then when we're 5 meters away, the intensity was 100. And so the question was, when you got out here to 10 meters away, so this was the first distance, here's the second distance. Now, what's the second intensity? Now, what I've got down here is complete example 4. Did I leave it at this point for you, or did I finish it completely in the video? Can you let me know? Okay, so it was probably at around this stage where I stopped and said, what do you think? So what's happening, of course, is that the source of sound is here, and that sound is spread out over the surface of the sphere. By the time you get out to 10 meters, it's a much larger sphere. So we definitely expect the intensity to be less. So the question is, what is the effect of doubling the distance? Well, if we look at the intensity, we see that it's power over 4 pi r squared. So that if we double the distance, there's a factor of 2 in there. So we're going from r to twice r. Now, when we square that, of course, squaring that 2 is going to give us a factor of 4, which we bring out in front. Now, I know I already have a 4 there, but I want to leave that. Because if this is the, and I'll just use a color here for emphasis, if this is the second intensity, this is the first intensity. And so what this little bit of algebra has shown us is that if we double the distance, right, if you put twice as big a number in here, you're going to get a factor of 4 in the denominator. So the intensity will be quartered. Cursor, there it is, sorry. So the correct answer is 25 watts per square meter. So that's true of all inverse square laws, like gravity and electric force and things like that. When you double the distance, you get a quarter of the effect. All right. Now, we solve this problem using proportional reasoning here. You actually have enough information. Like if you look at this equation, let's just write it in here again, right? Because we know intensity is power over 4 pi r squared. Because you know r is 5, you could actually solve for the sound power and then say, okay, it's the same sound power, but now I'm at a distance of 10. And you can calculate the intensities. And that was done at the top of the next page. So here we found the power of the source, and then we say, okay, we're 10 meters from that source, and you can actually calculate that 25 directly. It's not always possible to do that, though, so that's why we practice proportional reasoning. It's a little tricky as a thinking skill, but it's really important in physics. So I'm just there, and this is at the top of page 100 for you. So that's actually just in the notes already solved for you. It just shows us that our proportional reasoning was done correctly. Okay, so now, as I mentioned earlier, so sound intensity varies over a large range of powers in 10. So we introduce a logarithmic scale for that. And that logarithmic scale is called the decibel scale. Now, the logarithmic measure of intensity is just called sound level. And it's actually a dimensionless quantity, but we just put decibel in there as a placeholder so that you know that we're talking about sound level. This is a Greek letter beta. The way you do a beta is you do the tail and then you come up like that. Okay, so those are all betas. Beta. alpha, beta, gamma are the first three letters of the Greek alphabet. So what do? We take the intensity, we divide by this constant called the threshold of hearing, then you do the logarithm, and then you multiply by 10. So that's how you calculate the sound level. Here's some typical sound levels. They vary from 0 up to hundreds. Hundreds are very painful. I find when I go to movie theaters now that and I don't go very often anymore, I take my sound level meter, and then the sound is often like 100 and higher, which is dangerous for hearing. So I'm not sure why they feel obliged to crank it up so much. So logarithms, maybe it's been a while since you've done them, so let's just review the mathematics of logarithms in this example 5, which starts at the bottom of page 100. So we're going to find the sound level given an intensity. Let's just practice our definitions there and our labeling. Finding the sound level, that's beta that we're looking for. This is the intensity I in units of watts per square meter. So we don't have a lot of room, but this is a quick calculation. So first, we're going to, all right, I'll write it out, I guess. So first, we take the given intensity, and we're going to divide by this constant, this reference intensity, 1 times 10 to the power minus 12. Now notice that the units just cancel out there, which is nice. And then we're going to take the log of that, and then we're going to times by 10. So we do 7.85 E for, change sign, for, oh, come on, you, for negative. Okay, then we divide by 1 E 12 negative, put the equal sign, do log base 10, and then we multiply by 10, and we get 88.95. Now that's dimension. Let's write the only real units were in here, and they just canceled out. But we put a placeholder there just to say, hey, we are dealing with sound level. It's in dBs. All right, so now we'll go in the other direction. Say you have a sound level. How do you find the intensity? This is on page 101. I'll change the slide now. So there's 2 here. There's A and B, 1 and 2. I'll just do the second one here. And so our task is find the intensity. So here's the beta. Right, the beta is given, and what we want is the intensity I in watts per square meter. So we start off with the relationship. That, and so this is 52, the sound level is 52 in decibels. And I'm sort of switching back and forth there between the number and the variable representation. And so we're going to have to undo the logarithm or change from a log form to an exponent form. In order to do that, the 10, which is on the right-hand side, is a bother and an inconvenience. So let's divide both sides by 10. And now we're just going to change from log form to exponent form, or we're going to do inverse functions, however you want to call it. Log means log base 10. So if we change this to an exponent form, 10 is the base and 5.2 is the exponent. So it's 10 to the power of 5.2 equals I over, and now I'll substitute in what I naught is again, like that. The other way to do this, of course, is to realize that 10 to the power of is the inverse function of log. So if I do 10 to the power of both sides, I get the same expression. So it remains to cross multiply. And so for the 10 to the 5.2, we're going to have to use the y to the x key. So we'll have to do 10 y to the x 5.2, and then we're going to multiply that by 1 e12 negative. Oh, this computer calculator is terrible. Okay, so 1, 2, 3, 4, 5, 6, 7, 1.58 times 10 to the power minus 7. And now we'll put the proper units in, watts per meter squared. And there we go. So that's just a little practice with the logarithm and the definition of sound level. So we've done an example with the standing wave wavelength relation. That was pretty easy. Then we did another example where we used the sound intensity and pressure variation. And now finally, we've got the logarithmic measure of intensity, which is the sound level beta. It's time for you guys to try an example now. And this is just on the next page, which is, so I'm going to skip example 6, right, on page 101. We'll come back to that a little later. We're going to go to page 102, please. Sur la page 102. Change the slide now. And clear it up. Oh, no, that's example 6. Ha ha, not that one. Okie dokie. All right, so what do we got here? Ah, yes. Yes, okay, so we're not going to do this in groups. That's in the before time. So instead, we'll just ask you to ponder this example. Pay attention to the given information and try and correctly identify the quantities that you're given, right? For instance, 300 hertz, F frequency is in hertz. So you need to begin to know things like that pretty well. Okay, so we'll give you a little time to work on this, and then we'll display the solution. Then probably we'll take a break and then work on the problems for today, which are 1, 2, 3, 6, 9. right, so let's see how you're doing here. So in this case, you're given the sound level is 120. So that's beta. And from beta, when you substitute in 120, you can work backwards and find the intensity. Now the math should just give you an answer of 1 there. I'll bring that back down a little later, but that's just one of the first things you're going to need to do. So another thing you're going to need to do, because for the intensity equation, you need to know omega. So you'll have to convert frequency to omega, and you'll have to find the sound speed. Then, to find the amplitude of our molecular motion, A, notice in the intensity equation, we've got A. So if we can substitute in for intensity, density, omega, and speed, then we can solve for A. So that's our strategy. So that's what I've done here. I put in the 1 for intensity, which we found up here by inverting beta, and then density of air, omega, and sound speed. And so the only unknown there is the amplitude of air molecule motion. So that's the approach. Again, I'll just sort of hide that for a sec. We're not quite there, then have a few more minutes to work it out. All right, so hopefully you've been able to use the intensity equation to get the amplitude of air molecule motion. Then when you've got that, of course, the pressure variation equation just follows immediately. And so that kind of covers most of the ground that we introduced today. So let's, from here, take a break, come back maybe a little bit past 11 o'clock, and then we can work as we usually do on these homework problems, and we should have enough time to get them all finished here. And then just a reminder, I don't remember if I said this to you guys or not, but after class, take a break for a while, eat some lunch or something, and then you can sit down and you can add this class to your study notes so that you keep updating them as you go along. Sort of summarize the key ideas and then put down a key example or two. And something like this is a pretty key example. So let's take a break. And we'll